And I'm going to take another screenshot. All right, Sawood, if you're ready.
Sure.
Go for it.
Hello, everybody. I'm Sawood Alam from the Old Dominion University, presenting my doctoral dissertation on MementoMap, a web archive profiling framework for efficient memento routing, with my advisor, Dr. Michael Nelson, and distinguished members. So in this talk, we'll first introduce the problem that I'm tackling, and then I'll describe research questions. Then we'll discuss the overview of the MementoMap framework. And finally, I'll go through each of the research questions one by one, analyze that, and evaluate. And we'll close with describing contributions and potential future work. So starting with the introduction. This is the homepage of Smithsonian Institution. This is how it looks today, but it has not been this way always. So if you want to look at a prior version of this page, the obvious place to go for is the Internet Archive's Wayback Machine. And there, what you will find is a prior version or historical version, which we call Memento. You'll hear this term again and again. So just know that a memento means a time-stamped version of a web page. This memento is all the way from December 1997. Though there is a central image missing in this picture, which means the memento is not complete. It's not a very good memento. So folks at the Smithsonian Institution, they wanted to see their own site as it happened, appeared in the past. And they found an even prior version. The earliest copy they found was from 1996. That was from an archive called ArchivoPT. Not many people know about it. This looked more complete and even earlier copy. So it looks like web archives periodically capture the web in every site that they want that they capture it periodically. Now you have multiple mementos for the same resource over time. Different web archives represent that list differently. Wayback Machine on one hand is showing as a calendar view. On the other side, ArchivoPT is showing as a list. So how Smithsonian people found the first copy of their site? They went to a service called Time Travel, run by Lanel. That is a memento aggregator. In that service, not only they found the first copy from ArchivoPT, but they found copies in many other web archives as well. So far, it was great. The interface we saw is human-friendly. But what if you want to interact with these past versions or mementos from your script or your software? You need a machine-readable version. Luckily, Memento framework provides something called time map, which is a listing of mementos or URIs in a machine-readable form. We'll use these terms original URI or URIR and memento URI that points to a specific memento we'll refer to as URIMs. So here in this time map, all the URIMs are coming from the Internet Archive. Similarly, ArchivoPT also has time maps, and Memento is coming from ArchivoPT. But how about the aggregator? Aggregator speaks the same language as archives do, and that is Memento framework. So in this case, time maps looks the same, except with one difference. Here, mementos are coming from ArchivoPT, Library of Congress, Archive.it, and rest from the Internet Archive. So we built a command line tool to interact with mementos, and we call it MemGator. This is the only full-fledged memento CLI available as an open source tool. With this tool, what we found is, although Internet Archive has 13,000 plus mementos of Smithsonian Institution's homepage, but there are 10 other web archives that have copies. ODU's homepage, on the other hand, is not that popular, but it is still present in 7 archives. And if you look at the last line, that is like there is one copy from Icelandic Web Archive. Who would have thought that there will be a copy of ODU's homepage in Icelandic Web Archive? So why aggregate small archives? Wayback Machine has more than 1 trillion mementos, but it does not cover everything that web has to offer. Smaller archives often have unique mementos. They have better linguistic and geolocation diversity. Their curated collections could be more high quality than a crawler-based collection. And there might be restricted resources that are only available in small archives. So the MemGator tool that I demonstrated, let's describe how it works underneath. It has a list of known web archives underneath. And every time you query MemGator, it asks every archive. So basically broadcast that. And a few will return with good results. You change the URL, you look for ctvnews.ca. It asks every archive again, and a few responded. A third URL, same story. So this sounds very wasteful. While only a few are responding with good results, we are asking so many known archives. And to look into it, how wasteful it is, we looked at the 3+ years of MemGator's log. What we found is Internet Archive is the biggest and largest archive out there, but the MemGator AccessLog shows that only 1/3 of our requests were a hit there. MemGator doesn't necessarily reflect how humans use web archives, but it is how researchers used it. And over the period of 3+ years, what we found is collectively to 14+ web archives that we aggregated from, about 93% of the requests were wasted. They did not return any good results. So let's recap. What we want is to aggregate all the web archives, large or small, for good reasons. But the problem is it requires broadcasting, which is wasteful and problematic. What is the solution? We want a way to selectively poll archives that are likely to return good results for lookup URIs. And what do we need to do about it? And that would require basically creating profiles of web archives so we know what they have and what they don't. And how to do that? So allow me to introduce MementoMap framework. Suppose we have MementoMap framework, how it will work. The request that we send to MemGator for bbc.co.uk, instead of broadcasting to all URIs, it can look into profiles of all these web archives and creates a ranked ordered list of web archives based on their likelihood of finding good results there. And then MemGator can choose just a few top archives and request there. So how profiling is done? What are the strategies? In the past, Sanderson et al. In 2012, they created complete URIR profiling. And what they did is they use CDX files, which is like index of archives from many members from the IIPC community. So they created a complete knowledge of all the archives at that time. The problem was by the time the list was ready, many archives have already crawled more stuff. So keeping CDX files in sync is both technically and logistically very problematic and difficult. Olsum et al. Took another approach. They said, rather than profiling the complete URI, what if we only note down that archive A has .coms.co, archive B has .uk and .pt, and so on. So then we can route there. And this simple approach showed really promising results initially. But it had a lot of false positives. what we are doing is we are looking in the middle ground from these two extremes rather than um, taking complete URIs or just as little as the TLDs. We are looking for something like, how about every URI under CNN.com or every URI under .co.uk or bbc.co.uk being more detailed, or even further down if we go somewhere in the path like /images, and after that everything. So that leads us to our related work. The most closely related work was done in archive profiling field as an early exploration by Sanderson and Ulsom, and some work from our good friends at Lanel. Other related fields of our work are query routing, Bloom filters, web archive searching, archive web coverage, on-premise indexing, surface web crawling, deep and hidden web crawling, and focus crawling. So that sets up the problem and the potential solution that we may reach to. Let's talk about research questions. There are three major research questions. One is how to understand web archives. And by understanding, we mean what they hold and what they don't have. So holdings and voids. And then once we know what they have or don't have, how to express that, how to summarize and serialize their holdings. And once we have a way to summarize it and disseminate it, how are we going to utilize it for memento routing? So these are the three questions. And let's begin with first question. How to learn and archives holdings. There are two main approaches, content-based profiling and usage-based profiling. In content-based profiling, what we do is we looked at the CDX files, which is index of the archive. That gives a complete knowledge of the archive. Or externally, we can use full text search to discover what an archive has. On usage-based profiling, you can have a sample URI list and response cache. If you are running an aggregator for a while, you will learn from experience which archive has what and what it doesn't. Similarly, to learn about their voids, there are two approaches, content-based and usage-based. In content-based, CDX files are not helpful anymore here. So we need collection exclusion policies, access control lists that are specific to different archives. And usage-based profiling will be access logs of aggregators or archives. Then the second question, which is how to summarize and serialize archival holdings, we'll discuss about generation and compaction of these profiles or MementoMaps, and how to update and merge them incrementally or generate them in the distribution fashion, how to paginate in small chunks based on time or TLDs or separation between holdings and voids, and then how to disseminate it for discovery. Third question is the utilization of these time maps. So we'll create inverted index, we'll define routing scores, and based on that, we'll make decisions where to route, where not. We'll also look into a machine learning-based approach for classification. So the high-level overview of our MementoMap framework, basically it has three main components: ingestion, summarization and serialization component, and memento routing component. These three components nicely correspond to our research questions. The first one will deal with CDX files and full text search, access logs, sample URIs. The second one will talk about the resource constraints, like how much storage is needed and or transfer bandwidth, and application specific level of details in profiles, and how much time it will take to generate these profiles, that kind of thing. And in memento routing, we'll talk about the integration part of it, like how aggregators are going to consume these memento maps. For evaluation, we'll look into the cost, accuracy, freshness, and routing efficiency. In cost, we'll look into time, storage, network bandwidth, and so on. In accuracy, we'll try to see how fewer false positives and false negatives we can generate. In freshness, we'll discuss MementoMap of web archives need to be updated how often. And routing efficiency means when not talking about one archive, but multiple archives together, how efficient we are in routing to those places. So we took the complete CDX file from Archivo PT and our longitudinal access log from MemGator. And we tried to see a crossover between the two to see what people are looking for and what is in there in archives. So the first columns here basically represent number of requests in MemGator, that is x-axis, and y-axis is number of mementos in ArchiveOPT. So in the first column, we have 2 billion. What that means is there are 2 billion URIs that have about 1 to 9 mementos each, but they were never, ever requested. The bottom row means that 43 means there are 43 URIs that were requested thousands of times, but they have 0 mementos. And the other entry in the center, that means there are 45 URIs that have tens of mementos and that were requested hundreds of times. So this is how you read this, this chart. The first column is a blind spot for usage-based profiling. So if you are using AccessLogs to profile a content, you will not know about these mementos that are there in the first column. Similarly, the bottom row is a blind spot for content-based profiles. So these first column and bottom row are basically major source of false positives and false negatives that leads us to what they mean. So if mementos are present in an archive and their corresponding request is routed to that archive, that's a true positive. If they are not present and not routed, that's true negative. These are good cases. That's what we want. False positive is when an aggregator routes to an archive, but there are no good mementos there. So that's a wasted effort. And false positives are wasteful, and this hurt infrastructure, like all the way from archives to aggregators to users and everything in between. False negative, on the other hand, is mementos were present in archive, but they were not routed there. So it's a discovery problem, a disuse issue. False negatives are more dangerous. They are not good for users. For evaluation, we use recalls and accuracy. What recall is, given the subset of URIs that are actually present in an archive, and what percentage of that was actually routed there. This is basically recall. What accuracy is, all the URIs that were ever requested, whether or not they were present, how good we did in recognizing, correctly identifying things that were present and not present. That is accuracy. Generally, in people report precision and recall. We are not reporting precision here because in case of routing, true negatives are more important than anything else. Those are the big chunks that we want to cut down, and precision does not capture that true negative as essence. So with these metrics set up, we can move on to our research question and their evaluations, right? So the first part, how to learn about archives holdings. On top, we are seeing 4 variations of a URI. Some have HTTPS, others have HTTP, some have www in the beginning, some have uppercase letters in the host name, and there are some other variations here, but they all represent the very same resource. So if we convert it into an agreed upon version, that's called canonical URI or normalized URI. And from there, we make another transformation. We take the host part and we switch it around so the TLD or .uk in this case becomes the first component. And we do it so that the related URIs are together when they are sorted. So web archives use certs a lot in their index. And in this case, here is a sample index of a web archive. Generally, web archives store index in a CDX format or CDXJ format. These 2 pictures are these 2 variations of the same thing. The first column, which is highlighted here, that is the cert of each URI that are present in archive. If we extract it out from CDX files, then we essentially have complete knowledge of that archive, what they have. With these certs extracted, we can chop the URL off in smaller pieces so that we just have the prefix portion of it. So a group of URIs is represented together with a single key. And there are 2 different policies that we define, HMPN policy and DLIM policy. HMPN policy means in the key, we only consider at max M host segments and N path segments. So H3P not means 3 segments of host name. Anything beyond that, we'll chop it off. and path segment, we are not taking anything from there, and so on. So there are multiple variations on that. We evaluated 23 or so variations on that. And then delim policy, we only take registered domain, and after that, we just count how many subdomain segments are there, how many paths, and those numbers are put together. And with these techniques in place, we can create archive profiles that is illustrated at the bottom. So for each key, we can tell how many mementos are there in the archive, right? For evaluation, we used data sets from Archive.it, UK Web Archive, and Stanford. Stanford was a small data set. It was only for 1 year of their archive. Others were larger data sets. And then we created 4 sample URI sets, 1 million URIs each. So we can cross-check these sample sets in these 3 different archives. And what we found is the prevalence was very poor. They were like less than 4% were present in any archive. But their overlap was small, as illustrated in the Venn diagrams up on top. So when you combine them together, when you aggregate them, you almost get a sum of their mementos. So then we started evaluating. So we established a relationship called alpha, which is the proportion or relationship between CDX size and URI count. What we found is in UK Web Archives data set, we found there were about, each line of CDX file was about 175 bytes long, which means if we know the CDX size, we can directly guess how many mementos are there without counting those lines. Then we established a relationship between URIMs and URIR. We call it gamma. In case of UK Web Archive, it was 2.46. This is not a linear thing. It is generally curved a little bit. And the reason it is curved because archives revisit mementos, the URIs that they have already seen. And some URIs will die after a while. So archives will stop visiting them. That's why linearity is gone here. We then established the number of URI keys. So profiles are basically shorter version of list of URIs, right? How much reduction happens, how many unique URI keys you have as you profile more and more URIRs. And it turns out no matter which profiling policy you take, you get linear increase in that as the number of URIs grow. However, their slope will be depend on how detailed a profiling policy is. The generation time was constant, no matter which profiling policy we chose. It was mainly bound by the amount of data that we're ingesting, so it was IO bound. And we found we were generating consuming about 15 GB of CDX files per hour. So number of keys based on different profiles over the year from UK Web Archives data set. And each year the data set was growing in size. So that's why we are kind of seeing this kind of trend here. Now, the cost versus accuracy. Cost in this case is the storage cost or relative cost as compared with if we had to have like the complete knowledge profile, which is basically the list of URIRs extracted from the CDX file, no trimming done on that. What we found is most of the accuracy happens up to cost of 2%. Beyond that, you are already hitting 80+% of accuracy. So the increase after that will be not worth the effort. Then we kind of grouped together all these things that we evaluated. What we found is certain profiling policies go together. And H1P0 or TLD profile, that has nothing to do with how much data there is in an archive. It is bound by number of TLDs that are there, and which is like a few hundred or thousands of TLDs out there. But accuracy will be poor in this case. The second category has better accuracy with like 1% or less cost. And as you go bigger and bigger, more detailed, the relative cost will increase and accuracy will increase as well. When you go all the way down to URIR profiling, which was done by Sanderson et al., the relative cost and accuracy both go 1, and that's what we want. The problem is freshness suffers badly. It's very difficult to keep in sync. So far what we have learned is based on the complete knowledge of the archive. And complete knowledge means we need to have access to their CDX files. Here is the MemGator server that we are running. And right now it is aggregating from 16 different archives. And we really have CDX files from 4 different archives. That too are not in sync, those are partial. So keeping access to all the CDX files of on all the archives is problematic and not feasible at the time. However, some of these archives actually support full text searching, so we can leverage that to learn about their holdings. But that means we need to have good representative query terms for each archive, depending on their language or collection, so that we can discover URLs from there. But who knows the term frequency of Estonian nouns? And the point here is there are certain languages that are less represented on the web than others, and they have fewer linguistic resources available. So what we want is when we have access to a list of good query terms like top nouns, random dictionary terms, we can use that. But when we don't have access to those, we need to have a way to dynamically discover words for a collection and sail through the collection that way. And for this reason, we developed something called a random searcher model. And in this case, we go to archive it, you search for this term English or any other term that is relevant. It returns 20, 30 good results. And now we learned that this archive at least has these URLs. You put it down somewhere. Randomly pick one of these URLs and fetch the page, extract text from that page. Now you learned a lot of keywords that belong to that collection. Then you pick one of these words randomly, feed it back into your search engine, and you keep in circle again and again. And the central portion where you are learning more URLs, that will keep growing. Now, after a while, the return rate will diminish because you will start seeing URLs that you have already learned about. So the growth will not be linear in this case. And how you select these keywords from extracted text, do you want to select words based on their frequency, or every word has the same weight no matter how many times it appeared? Do you want to throw away pages each time and fetch new page? All these things kind of derive different policies. And these policies have associated costs. So static is when you provide external set of keywords. You don't have to fetch any pages to discover more keywords. So the HTTP cost is same as how many queries you are making. At the down, there is conservative approach where we use those keywords, and only when they are exhausted, then we fetch a new page to learn about new keywords. So these are good in cost-wise. Now, as I said, the rate of learning will slow down using Heap's law. And depending on which policy you are using for profiling and which technique you are using for operation mode for RSM, your rate of learning will differ. In the first case, when we are using TLD only profile, we could just make like 11,000 searches and we get to learn like 100% of the holdings of an archive if we use conservative approach. On the other hand, if we take static files, we'll go like hundreds of thousands of requests basically. And then now that we don't have complete knowledge, we have partial knowledge. So our accuracy and recall are not going to be that good in this case, right? If we use a smaller profiling policy like H1P0, recall will be good no matter how few you know about the archive, but the accuracy will suffer. On the other hand, if you have complete knowledge, the accuracy will be great, but recall will be, if you know 50% of the holdings, your recall will be 50%. So our suggestion here is to go for something like DDOM profile or HXP1 profile based on how much you know about the archive. Those will do good. So far, we have learned about what archives hold. Now let's move on to what they don't. And that leads us to archives voids. One would argue that if we know what an archive holds, then everything else they don't hold, right? And that's true. However, the whole point of profiling is to have summary of it, which is like a shorter version of it. So rather than listing all the URLs, you can just say, hey, I have enough copies of .coms. Now there will be certain section. In this case, Internet Archive has a lot of coms, but they don't serve Quora. URLs because Quora.com has blocked Internet Archive for privacy reasons. Um, Now, it would be good if we don't request Internet Archive for this because they don't show that. So there should be a way to say that this area is a void in this archive. And here, archival voids help us reduce false positives. So you had a detailed list, you shrink it down, you introduce more false positives, you shrink it down further, and you said, I have every thing at the root path of archive, uh, but not really, you don't have a lot of PDFs. So how you can say about that is that at the bottom, I'm showing, you can say, I have everything at the root path, but I don't have zero under the /PDF/ anything. So to analyze this, we use the access logs of ArchivoPT. And it was about 461 GBs of files, daily access logs of 6 years data. They introduced Memento support only in June 2016. So prior data was not very useful for us. And there were some other changes that are noted in here. And in that data set, what we found is we listed the frequent sites that that were being accessed. What we found was FCCN.pt was accessed more frequently, but it was coming from an automated service that was periodically checking, and it was a health check service, actually, Uptime Robot. Everything else is kind of counterintuitive. It's a Portuguese web archive. We would be expecting more PT domains will be accessed, but Google.com, YouTube.com, Facebook.com, all these .coms and .nets, .uk's are more popular than PTs. Another thing we noticed is there are two long URLs highlighted. Together, those were accessed more than like 22,000 times. And they always returned 404 not found. So if we had note of this somewhere, just by knowing these two URLs, we could have avoided those many requests to the archive. And this is the point of archival voids, right? So what we did is we extracted only 404 URIs that have never returned anything but 404. And what we found is that an archival void profile of about 2.4K URIs that were accessed hundreds of times or more could have saved about 8.4% of wasted queries. So here are a bunch of recommendations based on our understanding of how archival voids work. We think it's better to keep archival void profiles separate from archival holdings so that it is easier to update on archive side and also on the client side. Also, these should be updated more often than archival holdings. Use specific keys with only high confidence. Don't be too big of an umbrella unless you are really sure you don't have any content there. Profile only resources that are high in demand. Profiling things that are not in demand is not going to yield any benefit. It will just increase the size of the profile. So moving on to our next question, how to summarize and serialize these archival holdings and voids, right, for dissemination. And for that, let's look. If only archives could tell what to ask them for, right? But this is something that already happens in regular websites. They use sitemaps so that search engines can know what URLs they have. The problem with sitemaps is they don't scale on archival level, and they would go very stale. This is the same problem as URIR profile, right? Robots.txt, on the other hand, has this compact syntax, but that's for exclusion, and it assumes single domain, not multiple domains. That's quite the opposite how archives work. Well-known URIs are a good way for discovery of domain-specific metadata. So if we combine these three ideas, what essentially we get is MementoMap, and that's the framework we are introducing. So what a MementoMap looks like, this is how it looks like. And notice that we are using star signs all the time here now. We get away with the HMPN policy and DLIM policy, all the static policies that we described before. And the reason we get away with that is because those were great for baseline evaluation, but they are not good when you are trying to combine profiles of different policies. So we got to this more flexible approach here. And for that, we had to extend certs with this asterisk sign. This is our contribution to that. So what you are seeing here, on top, there are some metadata lines. And after that, we have a star, which essentially means there are about more than 54,000 mementos of 20,000 URIs in an archive. The other line says there are more than 10,000 mementos of .coms, and so on. That's how you read it. So if you have the list of URIs insert format from an archive, whether it was extracted from the CDX or learned from URI sampling or full text searching or whatever, you can organize that in a tree structure where first top level is the scheme and then host and then path and then query parameters. And these asterisk sign are kind of highlighted with these triangles. That's what it means really. And this is again an extension that we made so that we can perform dynamic profiling. What we found in RQPT's index that we use for evaluation, that there were about 5 billion mementos of 2 billion unique URIs. We used that data set, and what we found is RQPT was created to archive sites of interest to the Portuguese people, but 1/3 of RQPT is other than PT pages. Hence, routing based on top TLDs would miss a lot. Who would have thought that RQPT has more than 10,000 sites from this Russian TLD, which essentially means .online in Russian. So we looked at their URIM and URIR growth over time in RQPT. What we found is they are growing with a exponential rate. In the last 2 years alone, they have increased their mementos. They doubled it basically. Another thing we learned is like over the time, they were learning new URIRs at a steady rate and also revisiting prior mementos. So the tree organization that we described before, if we take all their URIs and organize in the tree structure, on the left-hand side, we have host names. On the right-hand side, we have paths. Kind of shows how URIs grow at different levels. And what we found is up to host level 4 is where all the growth happens. After that, it doesn't grow a lot. In path segments, up to P6 is where things go substantially down. There are not many URIs after that. So this shows what are the attack surfaces where we can cut down and make some adjustments to reduce the size of the keys. And this is how it happens. So on host and path, both segments, when we start pruning from the bottom, this is how the overall number of children or keys reduce in size as we go from one level to the other. We introduced a MementoMap generation and compaction algorithm, which is a linear single pass memory efficient mechanism to generate MementoMaps. And the way it works is the output file it generates, it ingests a list of URIs. It grows linear, and then when there is a roll-up happens, the output size drops down, and then increase again and drops down again. So that's how it increases, but overall there will be a growing trend in here. With this dynamic style of MementoMap generation, with different weights and what we generated were like different levels of details, basically, in this dynamic rollups. And what we found is the winner was, with about 1.5% relative cost, we were able to have 60% accuracy. And that basically means ArchivoPT could just have released like 120 megs of file, and that would reduce 60% plus of traffic. So how to disseminate once you have these memento maps created? Once standardized, this well-known URIs can be used where people can look for to find memento maps of specific archives. Or if there are relationship types standardized, then HTTP link headers or HTML elements can be used for the same. Then with this, we can move on to the next research question, which is the final research question: how to utilize these memento maps for memento routing. So putting all these archival holdings and voids together to combine these memento maps and create an inverted index, then define a bunch of scores and predict their existence in certain archives. Here, what we are seeing is we have this long URL from ODU. We want to see which archive to choose if we have two options. One says, I have only one memento or one URIR of a URI that falls under odu.edu/star. Now, it could be this URI that we are looking for, or it could be something else. Another archive says, I have 10,000 plus URIRs that fall under odu.edu. Which one we should go for, right? Obviously, it is possible that the first one was exactly this one, and the second one is missing this URI. But from statistically speaking, the second one is more likely to be found. We define this essence of this aspect as density score, which basically says how much effort an archive is putting in a specific subtree of our URIs, which is a ratio of number of URIRs under a subtree, URI subtree, divided by all the URIRs that archive has. We are using log scale here so that the numbers don't punish large archives. Moving on to the next aspect, looking for the same URI. This time, both archives have said they have 100 URIRs, but both are returning different levels of matches. One is saying the root path, and after that, everything. The other one is says it has a lot in common. It has a longer key that is prefixed matched with the lookup URI. So I think it's wiser to say the second will be a better candidate for to go with this, right? And we capture this essence as closeness score, in which we consider the length of the matching URI key prefix and the difference in the lengths of the two URIs. What we are actually looking for is a way for multiple archives to have a score based on which we can decide a heuristically decided cutoff threshold. And then for a URI, we can find, hey, these are above threshold, so it is likely to be found here in this archive, and these are below threshold, we are not going to find in here. And we define this score as routing score, which is a combination of mu and chi, which is the other two scores we just described, the closeness and density. But that is for one archive alone. When you have multiple archives together, you want to combine them. And for that, we have something called relative routing score, which will be a number from 0 to 1. And that will allow you to rank order these archives. But some archives, for the same score, will give better results than others. And for that, we also have weighted relative routing score that will allow you to adjust your preferences or weights for each archive. With these scores defined, here are three different memento maps. One that has both holdings and voids. The other one has just holdings, and the third one has just voids. We can combine these memento maps together into something called inverted index. These two are the same things in different variations. The one top one has basically keys followed by the URI, the archive they belong to, and the density score. But the other one basically combines them together. If the keys are same, their archive and corresponding score can go in a JSON block here. The second one more closely matches how inverted indexes are done in traditional information retrieval systems. And this is something that we can use for quick lookup, and then look at the scores and decide where to route. And for that, after looking these inverted indexes, what we'll have is we'll be creating a result that will look something like this. At the top, we have something, archives like Internet Archive. We don't want to profile that. That's too big. Okay, but we don't want to it to disappear from the list, so we always give it a default routing score. At the bottom, we have things that have matching archival voids, basically. So now, given this list, a client can decide which one of these archives they want to go for based on routing score or relative routing score, whichever they choose. With these numbers in place, we can evaluate them, right? So ArchivoPT, we got access to their access log. We were able to identify their archival voids, So we created their archival voids, like 2.3K keys generated from there. But for other three archives that we used for evaluation in the past, we don't have their access logs. So for that, we used access log of our MemGator, which is an aggregator. And we use voids profiles from there. The number of keys are smaller in that case, basically because we don't have that extended log. So one thing we looked at is how archival collections diffuse over time. ArquivoPT, being a Portuguese web archive, we would have thought they'll have more .pts, but there are only 61% of holdings belong to .pt. Archivit is a subscription service where libraries and educational institutions are members, so we thought .edu and .gov are good candidates there. But that has only 12% prevalence in their collection. .coms, .orgs are more prevalent, actually. UK Web Archive is the tightest when it comes to their collection diffusion. Their 99% collection is just UK. Stanford Archive had less than 1% URIs from their own university. But the situation might have changed because we only had data when it was only 1 year old. So we got all these data sets and scores. Let's do some routing and evaluate that. So in the first line, we have random 1. What we are doing here is, let's not use any score for now. We got n archives, and we have r requests coming to an archive aggregator. What we do is we randomly choose one archive and route there. What will happen? The recall will be 1 upon n, but the score is a little more than 25% here because there are some overlaps between these archives. So the score is a little higher. But the accuracy is really poor. And the reason is we are making requests to top archives even when there is nothing in there. The score is not deciding that whether or not you are going to pull from somewhere. In case of random 2, recall is doubled, but accuracy remains as poor as it was before, and request cost actually doubled. Go all the way bottom, the broadcasting, recall will be 100%. We are not going to miss anything that is present in any. But then request cost goes all the way up to n times r, and accuracy is still poor. So then if we use the routing score that we defined, and we use top 1, doesn't matter how many archives it is present or not present, we just use top 1. What happens is recall goes significantly high, but accuracy is still poor, but it's much better than the other 2. So that was the baseline style. How about cutoff-based threshold routing? Here, we found that we can have a recall of 89% with accuracy 96%, or pump up the recall to 99%, but the accuracy will go down to 68%. So there is an inherent trade-off there. We also noticed that inclusion of wide profiles improves savings, like request savings, more than the accuracy. Accuracy increases, but the savings increase even more. And the reason is because wide profile are all about more frequently accessed URLs. Then we also looked at a machine learning approach. We supplied this data to a rudimentary machine learning system, a Bayesian classifier. What we found is it was giving good accuracy, but recalls were poor. And the reason was prevalence was small, like 2-3% of the lookup URIs were present in these archives, which means if the classifier were to say not present, not present, not present all the time, it will be accurate 97%, 98% of the time, right? So that's why recall is poor here. So that wraps up our evaluations. Now we move on to our contributions. And first up, in this many years of work and dealing with petabytes of data and doing all sorts of evaluations and analysis, we needed and we created all sorts of software and tools, and we released them publicly as under open source licenses. Our tools and scripts affect various aspects of web archiving ecosystem. One tool in particular, MemGator, has served many other researchers and practitioners in their work. So moving on to our algorithmic contributions, we have introduced random searcher model, which utilizes full text search interface to sample archival holdings. We also introduced MementoMap generation and compaction algorithm that consumes sorted list of URI sorts and yields MementoMaps. It's a linear single pass, small constant memory footprint algorithm, irrespective of the size of the input. There are a bunch of terminologies and metrics that we introduce, like URI keys, archival holdings, archival voids, relative cost, and a bunch of scores like frequency, density, closeness, and routing. For each of our research questions, we have a bunch of publications in various venues. Two of our posters were awarded as Best Poster Award, and one of our long paper was nominated for Best Paper. Some publications are still in line to be published by next year. And with that, we can say that MementoMap framework opens up gates for a lot of interesting research going forward that will be based on what we established here. Things like URI keys can be used for seed summarization, archival voids for assessing crawl jobs. UKVS file format can be utilized in different places. We have profiled only URIRs, but date, time, language, and other aspects can be profiled as well as application emerge. We also think there is a need for standardizing across archive collection exploration. For example, many web archives these days are collecting COVID-19 related web pages. Now, there is no good way to find all those collections across archive. That's an interesting aspect that should be explored in the future. Alternative approaches for URI subtree rollups and some more machine learning approaches for Memento routing can be applied on our data. Then I'm also interested in hierarchical network of Memento routing, especially because aggregators behave like archives. They speak the same language, so they can be chained. And as more and more archives emerge, that will be a good thing to look into. Adoption of MementoMap framework would be something that will make me happy. So here is the path of adoption. Numerous web archives, archival replay systems, and aggregators have shown interest in that. Big web archives can start with publishing archival voids. Internet Archive doesn't have to, it's too big. Archives with access restrictions can have multiple Memento maps. Third parties can create and publish Memento maps of the rest of the archives while those archives catch up themselves. So this is what is next for the Memento map. What is next for me in my career? Well, I have joined Internet Archive Wayback machine team as web and data scientist. So if you plan to do any research with web archival data or services from the Internet Archive, I'll be your research liaison going forward. And now allow me to conclude all that we talked today. We first introduced the challenges in Memento aggregation. We described that broadcasting can be evil. Profiling is desired for collection understanding and better Memento routing. Aggregation is useful even for small web archives. And then we described MementoMap framework that addresses our three primary research questions about learning about archival holdings and voids, serializing and summarizing them for dissemination, and then utilizing those Memento maps for Memento routing. What we found is we achieved over 96% accuracy with 89% recall and 68% accuracy with 99% recall via about 120 MBs of MementoMap file of an archive which has more than 2 billion URIRs in it. So with that, thank you so much for paying attention and listening, and I'm open to questions.
Okay,
Right. Thank you, Sawood. At this point, we'll take questions from the audience. So you can either shout it out or put it in the chat box and we'll get to it. However you want to do it.
Okay, I'll go ahead and go first.
Yes, Sean.
slide number 60. No, sorry. Slide number 79.
79. Yes.
Could you explain this better?
Yeah, to actually realize it, you'll have to read my dissertation. But what it is actually is, yes. H naught is basically just the top level, the starting point, let's say scheme portion of the URI, right? So there are only HTTP or HTTPS, right? But we call it one because it is considered as one. From there, from H1 to H2, what you have is about, it goes from 1 to 973. Those are all the top level domains in RQOPT. So if there are 973 TLDs, your URIs go from one scheme all the way to 900 plus TLDs. From there, it will expand even further in the second level generally registered domain, like CNN.com, foo.com, example.com, and so on. These will fall in H2 level, okay? So how those URIs will grow at host level. And the reason is their shapes are a little different is because, look at H2 line here. The green box is, it starts from 904 or so TLDs, and it goes further down to 2.1 million registered domain or something like that. Some of them will expand further, and others will go all the way directly down to path, basically, right? So that's why that is in the center. It's kind of a visualization trickery that I used. On the other side, in paths, when you go to P1, and after that things terminate, so the outside cut-in portion is basically where URL terminated. The central region expands to further. Some portion will terminate there. Some URIs will expand even further in more path depths and so on. So this is what it is visualizing. Also, the path segment is kind of a scaled down version, 170 times scaled down. If you expand that 70 times and attach it underneath the host name, then you will get the good full picture how things look like, basically. But then it will not fit in here, right? Does it make sense?
I think so.
But yeah, I mean, for complete realization, you'll have to really read the doc. But yeah, so let's give an example. Okay, if you have CNN.com/news, okay, what will happen? So you got HTTP, which is H0, okay. In H1, you got com. H2 is CNN, but it doesn't have any more subdomains or anything, right? So you are in the center of that dark green thing, basically. You jump down all the way to host because there is no URL that does not have any paths, okay? No matter what size of host is, there will be a path associated with that, right? And path in this case is /news. So slash is P0. P1 is /news or whatever. If it was /news/international, then we'll be somewhere in P2 if it goes there. If it terminates there, then you are at the outside of the portion of that tree where it ends, basically.
So what are these numbers on the right? Are these minimums and maximums?
Yeah, no, that basically means from, say, from P1, let me, so the child node, how they emerge from there. At P1, for example, at 5.8 million children nodes at that, parent nodes there expanded into 14.6 million. Now all those 146 million paths, those were extended in the next level. But in the next level, we are not using all those 146 million. We are using only 40 millions that are going further down. Remaining 106 million were basically ended at path level 1. Make sense?
So the 40 million is included in the 146 million.
Yes.
Okay, got it. Okay, so, yeah, that makes sense.
It looks like this. There'll be some parents that will have child. There'll be some who will not be fertile. They won't have any children, right? So those are the outside ones, basically. If you subtract the starting point of one level from the endpoint of the prior level. That's what you get the number of nodes that don't have any children anymore. That's where the URL terminates, basically.
It's a cool visualization.
Oh, yes. I wrote some D3 for that.
It's pretty neat.
All right, next we have Alexander, and then after him, Mark has a question. Alexander?
Thank you very much, Sawood, for your talk. Before my question, I would like to say thank you very much for helping me throughout my PhD work, and all the advice, all the hands-on helping was very instrumental to me succeeding in my program. So thank you. Then my question is this, does your whole framework is based on, does the current way the web archives work, which means you need to know the URI you're searching for, then you go to whether your aggregator to the web archive and you search for the URI. Now, there's this, recently, there's, I know you're more familiar with this, there's this movement of trying to search using maybe keywords, just as we'll do a traditional search engine. My question is, do you see any aspect of your framework being useful if there's this move toward now using keyword terms to search for people and entities in web archives as opposed to the standard URIs? Is there any form of this, your summarization of this profile, that would be helpful to such a framework or such a system of access to web archives?
So that's an interesting question. And the thing is, let me explain a little bit of difference between search and lookup. In lookup, you already know the key that you are looking for. And the answer is, it's found or not found. Okay. In search, there could be 0 or more results, and those will be ranked and prioritized. So that's one difference here. All the URI-based lookup that we do is primarily really lookups. You need to know the URI in advance. And Internet Archive and other archives, smaller archives are actually doing full text searching. Doing it on the scale of Internet Archive is problematic. We are still working on it. But once you have that thing solved, this problem goes back into the traditional how digital library search works. You have books in ODU, you have books in your university and in some other universities. How you can perform search in one place and find resources in other libraries, and you can get that from interlibrary loan and all, right? So someone needs to index those things, right? And there are all these aspects are already deeply researched actually in the past, where do you want to perform indexing in one centralized location and you index all these archives there, or you want to forward the query to everywhere and let those archives perform searches and give you results back, basically. So I think, of course, on the practitioner level, there will be some work that needs to be done, and whatever is the unique aspects of archive that needs to be put in place. For example, there is temporal dimensions in archives that is kind of unique. But otherwise, the rest of the problem is already actually solved academically. And definitely there is an overlap, and things can be, one thing that I mentioned in the future work was collection exploration, for example, which is again kind of a form of keyword-based searching, but it's more like at a collection level rather than individual resource level. And I gave the example of COVID collections, that different archives are collecting that, but then there is no good means of, now if you want to see how many archives are there that are collecting resources for COVID, there is no good way to kind of find that, unless you go to, the blog posts posted on IIPC, there you'll find some. But that's not the, but yeah, you have raised a very interesting questions. And I think academically, a lot of that problem has been solved in the context of digital libraries. But there is certainly some thing that needs to be explored when the time comes.
All right, Alexander, is that good?
Yes, it is. Thank you.
All right, next, Mark had a question. Mark, do you want to verbally state it?
I can summarize it, but I wrote it there. Yeah, I mean, going back to the problem you were trying to solve, did you, at the end of the day, do a comparison, like an A/B comparison of, say, some random sample of URLs and submit them to the existing time machine system and the existing ordering versus the optimized version and just see, hey, did this help?
So we did not do that. What we did actually is we had access logs, complete access log of RQOPT, and we have complete CDX files. So we already knew their entire knowledge and how they evolved over time, like year by year. Okay, so we could just replay that behavior without going through because we are not interested in crawling aspect of it, how well an archive is crawling and all. We are just whatever you have, how well we can discover that you have basically. Does that answer the question, or you are asking something more specific?
You answered the question. Thank you.
Yeah. That does point to a future evaluation that we could do, right?
Yeah.
Instead of just looking backwards with data we know to be true, we could, given this information, apply it looking forward. Other
Indeed.
questions from the audience? You know, everyone being bashful. Other questions? All right. If there are no other questions from the audience, shall we begin with questions from the committee? All right, Mark has another question.
I was just wondering, can you access the CDX of archive.today? Is that even possible?
That would be awesome. Let's ask them, right?
All right.
Yeah, well, they don't even have CDX, right?
I mean, some form of index, right?
Right, they have something, right? But yeah, but yeah, that's a complete black box where you need to throw queries at it and see what comes back, right?
But then we have full text searching. I tried using their full text search query. They're providing lookup, basically URI lookups. But when you perform full text query using like random keywords, they actually report web archives, internet archives results. That was surprising to me. I had no idea what was going on.
I didn't know about that. I'll have
Yeah.
to look at that. Yeah. All right. Any last chance for questions from the rest of the audience? All right. We'll proceed to questions from the committee. Who wants to go first?
I can go first, but
All right.
Michael,
I can always count on you.
yeah, thank you. Question, I mean, are we allowed to keep all the audiences here, or?
Yeah, for this round of questioning, yeah, everyone's here for this. Yeah.
Okay, then I will keep my questions later for the committee only.
All right. Other questions from the committee? Dr. Jayarathna.
So yeah, I have a couple of questions.
Please.
So can you go to the slide number 34?
Yes.
So can you talk about the 34 and also go to 37?
37?
So I'm going to just based on those two. So can you talk about why, and also 38. So if you go to the 38 also, like, let's go to that, so we can kind of start from there. So you said that we do not report precision because it does not capture true negatives. So can you explain why this particular decision?
Yeah, okay, sure. So in traditional information retrieval systems, you care more about the good results that you found, right? Here, good results being things that are present. But it is equally important in this case to not have bad results, right? So if we go here, for example, in this confusion matrix, basically, what happens is, actually, if you look at the level of what they call it, the prevalence, only 3%, 4% of your queries are going to have a hit in an archive other than Internet Archive. In that case, your focus is better spent on identifying more accurately things that are not present so that you can cut that down. And that is true negative, right? And that is in traditional information retrieval, where you are trying to retrieve documents from a big collection, you are focusing more on relevant items. Here, you want to more accurately and more aggressively identify non-relevant things so that you can throw them away. And that's why precision is basically, it's a area that you basically identify, which is the top row here, true positives plus false positives. Right? No, true positives plus, yes, true positives or false positives, that is going to the denominator basically, and in numerator, your true positives are there. So false negative, which is a big chunk, that is cut down all the way. And that's basically, sorry, true negatives, they are going to increase your overall accuracy. You just don't consider that. So what you are saying is, when you are talking about precision, you are saying, given all the things that we predicted, how many of those were predicted well? That is the essence of accuracy. It does not talk about things that you did not predict or predict that those are not present, how well that decision was. Does it make sense?
Okay. So you talk about the associated cost, right? In this case.
Right.
So
Okay.
So one thing is that I think you kind of somewhere down the line, 50, you kind of in slide 50, you talk about the cost. So no, I think yeah, somewhere there, but not necessarily, but that. So the problem is
this one.
So what I don't get it is that specifically when you're looking at the false positive and false negative, like we call it like type 1 and type 2.
Right.
Which one do you think, like, so I know I was kind of reading through the dissertation, one thing that you mentioned is that in terms of the cost, in terms of the false positives, what affects is the infrastructure, so the wasteful infrastructure cost.
Right.
But when it comes to you're looking at false negatives, the problem is that it affects the users. But my question is, in terms of these costs, which one do you think more important for us? I know which answer that you're going to point to, but just to make sure it is clear, what battle that you're trying to pick.
Right. So I think I kind of summarized it here. False negatives means things that are present in archives, but your aggregator did not point to that archive, right? So you kind of have this disuse thing. Resources were there, but you did not discover that, right? So users suffered because users could have accessed that resource that they would otherwise not find, right? And this cost, in our mind, is more, prominent, and I think we should be trying to minimize false negatives as much as possible. In fact, if you have read my dissertation, in most of the chapters, when I was doing baseline evaluation, I tried to keep false negative 0. We did not introduce any false negatives, and we got like 60% or so accuracy while still keeping false negatives to 0. So not missing anything, just by focusing on false positives and improving on true negatives, basically identifying things that are not present more accurately. We're able to cut down enough traffic. In fact, even if the the precision, if you were to report it, and if the precision says we got 60% precision, that's a very good precision actually, because depending on how well you did on true negative side, that's where the saving happens. The reason is prevalence is so small, so things that you predict are going to be way smaller than the sample size anyway. And what is happening in the rest of the space, is more effective. As you said, which one is more serious? I think false negatives should be considered more seriously, and we should minimize those as much as possible. False positive, yes.
Sawood, I actually, this seems like a good place. I think you still have it in your backup slides to tell the Library of Congress story with,
yeah,
with Gina Davis.
Okay. I forgot that I had backup slides. That's here, right here. Okay, yeah. So what happened when we created this MemGator tool? After a while, oldweb.today is a service that was launched. They are utilizing MemGator inside. And since MemGator by design is using broadcasting to everyone, what happened is oldweb.today's launch was taken by storm. And there was a lot of requests going to all these 12, 13 different archives that it was aggregating from. So Dr. Nelson received an email from Library of Congress. They were saying, hey, it looks like there is something called MemGator that has your Twitter handle, basically, which is causing a lot of trouble to our servers, basically. So Dr. Nelson replied, oh, looking at the traffic, it looks like it's not us that are causing that traffic. It's MemGator is a tool that is being used by oldweb.today, and they are causing that trouble. So one day later, we received this complaint, this note from Ilya Kramer, who is the creator of oldweb.today. He said, hey, I was asked to remove an archive due to the traffic it was causing temporarily. And that kind of ties things together. So this is where we really need to focus on cutting down the broadcasting aspect so that smaller archives can flourish while they can still serve the good content they have without dealing with a lot of traffic. In this case, obviously, the false positive being trouble on infrastructure, as I said, the wasteful traffic is a problem here. But the thing is, once it is excluded, Library of Congress is excluded, all the good things that they have that won't be discovered anymore, and that's a disuse. So that's where I think our framework kind of comes into a picture where you minimize the waste while still maximizing the yield for users.
Mm-hmm. So I agree. But in terms of the evaluation, right, this is something very hard to kind of simulate in this, because what you are trying to do is a closed evaluation study, because that's how that you can come up with these numbers, right? Mm-hmm. Metrics. But what you have is like you're trying to maximize the part where not getting false negatives. But your evaluation kind of focused on in terms of the cost is mostly about the infrastructure, right? So what, how you did to kind of simulate this negative part on the user, like, in terms of the evaluation. So that's what I mean. So I knew that you're going to say like, yes, it's important. The users are important because pointing them to the data that's not existing in the archives, is problematic. But your evaluation basis is mostly about the infrastructure, like looking at the cost in that, slide 50. You're comparing a lot of the accuracy in terms of the cost of the infrastructure.
So allow me to actually point out again that in many of my chapters, while I was trying to minimize the cost, cost in terms of storage, cost in terms of generation time, cost in terms of false positives, I was keeping false negatives to 0. I was not introducing a single false negative, like recall 100%. So I think I was very careful there in making sure users don't suffer. It's in the last chapter where we are started to kind of, route things. That's where I kind of allowed some false negatives as well. And the point there was, hey, in fact, if you go to my summary slide, where I say, I concluded actually, let me see, where it is. So here, what I'm saying is, I'm giving two pairs of accuracy and recall. We want to maximize accuracy, but not at the cost of recall, right? So sure, if you want to maximize the accuracy to 96+%, recall will go somewhere around 90%, but then users will be losing 10% of the resources. But then in parallel, we also said, hey, if you can compromise a little bit of accuracy and go to 68, 70%, we still have 99% recall. That's really good. We are only losing like 1% of recall, right? And even if you don't want that, you can be even tighter. And that's already evaluated in prior chapters, where we introduced like, some 60% accuracy or something like that, with 0% false negatives. That is 100% recall. So it's there. And I think at the end, by giving these knobs, we allowed end users to choose what is important for them. If I'm running an aggregator, and by hurting 1% to users, if I can have like 40%, 50% saving on my infrastructure, perhaps that's a good compromise I might want to take. But if individuals are trying to use aggregators, so for example, MemGator is as an open source tool, you don't have to rely on one infrastructure-based service running. You can run your own for your own analysis if every single thing is important for you, and you can do broadcasting or go with a more conservative approach to not introduce any false negatives. I hope that answers.
So related to, let me ask you this question. Are you familiar with something called the cost sensitive analysis?
Say it again?
Cost sensitive analysis. So basically it's that related to the measurements that you are coming up with your confusion metric. So I want you to think, because you're trying to, give this idea that it's important, having the false negatives, having the false positives is problematic, but you try to kind of make it zero, minimize, in terms of the user. So if these are important, what I want you to kind of think a little bit, maybe to complete your dissertation, is that look at how you can involve the cost, because what you're providing at this point is just that you have the accuracy, you have the cost, you don't really necessarily connect them together. So what the cost sensitive analysis does, basically, it's kind of very simple. The idea is simple because what you have is a very close sort of a evaluation study. So what you can do is that put numbers, because you already know what are the costs associated with it. If you kind of have the idea of the infrastructure that's going to be utilized in this. So the idea of that is, if you are really worried about the false negatives, you can put higher cost to it. So instead of just looking at the accuracy values, so now you can actually look at another metrics. So it's very similar to the confusion metrics. What you can do now, you can put like getting true positives, getting true negatives, put like -1 or 0, whatever the lowest cost. And then whenever you have cases where you're getting true negatives or false positives, put the cost that you can measure, and then you can generate a cost value from each of the methods that you are evaluating. So when you do that, you can now have two things. You have the accuracy plus you have the cost associated with using particular. Sometimes, accuracy gonna be better, but you have higher cost from that approach, because that way you can tune in which way to kind of go, right? So that's something I'll give you a little bit more information later, so that you can kind of add, because you already have these numbers. It's a matter of just plug it in and
so. Is that a feedback loop kind of thing? You learn
exactly.
as you go? Okay, got
right,
it.
Right, exactly. When you're evaluating it, it can give you a better connection to the cost, because right now it's loosely connected, right? You have the accuracy, you have the cost, but you don't really connect them together to tell the story. How your different methods going to perform. Because you're reporting them separately. Yes, you're putting it to plots, you're trying to get charts out of it, but it doesn't really say like how they are connected, right?
So for example, in this slide, by moving the cutoff threshold up and down, an infrastructure provider or aggregator, for example, or any tool that is consuming, they can control how much true positive they want to tolerate. And that will, there is kind of inherent, if you want to minimize false negatives, false positives will increase basically, right? So depending on situation, they can just change the cutoff portion in one of our tables, basically, right here. That's why the threshold, we checked at different thresholds, and that's where basically you just adjust the slider and you find different metrics here, obviously. So the point, I think, of this research was to kind of demonstrate that there is a this kind of a relationship, and here is the tunable parameters that whoever is operating these things for whatever purpose, depending on the application and how much infrastructure cost that they can bear, they can use it like that. But again, I think what you are indicating is kind of opens up a whole new window of opportunity. For example, not only cost to individual aggregator, but for example, if we know Internet Archive doesn't mind getting more traffic, but Library of Congress is more sensitive, we can actually fine tune to individual archive level, okay? So one false positive to Internet Archive doesn't cost as much as it costs to, say, Library of Congress, because they complained in the past, right? Smaller archives are more sensitive to how much they can handle. And this is actually in web crawling, for example, there is this behavior. Crawlers, when they are crawling the web, they try to keep a slow pace. They don't want to make 500 requests in 1 second to the same host name. Though they can, they have all the infrastructure. But the other end, the poor person's homepage might suffer to have so much traffic at once. So they introduce something called politeness factor. And that sometimes they have like an umbrella thing, like default value for each website. Sometimes they adjust it over time as they learn how the site started misbehaving. So let's slow down. There are other ways, like in sitemaps.xml file, there is an extra parameter where webmasters can tell, robots.txt file, webmasters can tell, hey, we want you to at least have 2 seconds or 3 seconds of pause between two consecutive requests. So I think you are pointing to a very interesting direction, and that will be a very interesting future work, I guess.
Yeah, exactly. So because that way these individual, archives can, because they know the cost associated with their infrastructure, the cost associated with not, pointing to the correct memento. So because they know that they can apply the metrics on top, the values that you are giving from here, and they can calculate, how to fine tune which one to kind of choose. Good. Yeah, that's all from me.
So I think, let me point something out here. In the metadata field of MementoMap, I think this is a real opportunity to define a keyword that specifically means this, where archives can tell, hey, here is my MementoMap, and they can tell how often I update it, okay, so that the whoever downloaded their MementoMap, they know where they want to come back and refresh the MementoMap. Otherwise, they will have to periodically poll, basically. Archives can also tell here, with the help of predefined metadata attributes, like, oh, this is the politeness that I'm seeking from you. In fact, they can just also say something like that in the robots.txt file or something like that.
All right, so we're going to move along to the other members of the committee. Next up, Dr. Frydenlund.
Thanks. So I just want to preface this by saying that I am a social scientist, and I thought your dissertation was really well written. I have 1,000 questions that probably are just because I don't really know your domain. But I think thematically, my questions are, not to offend everybody, but This sounds like computer science, like archivist stuff for archivists. And I'm curious about what's the bigger picture? Like who else uses this? Who else benefits from this type of work?
Oh, interesting. Yes. So the field in general is kind of narrow and focused. The immediate beneficiaries will be web archives, especially smaller web archives. And I think the mantra of this work is to allow smaller web archives to flourish while their content being exposed. And so it happens with, I mean, you are a social scientist, you know it better. When you have a collection of any sort, you want the world to utilize it, right? You have an archive of artifacts or music or whatever. You generally want the world to know and get access to it. But if you're too small, that you don't have a big office in New York, not many people will have access to your material. What this framework actually allows is to exposes even little players in the game, while not causing too much trouble to them in their operations. I hope that kind of addresses some part of the question. Other thing, who else can leverage from a broader perspective? There are bits and pieces in this work that can inform in other disciplines. For example, file format that I introduced that can be useful in any field where they have key and value style storage, and there are already millions of file formats to handle those cases. But our approach has some unique features to offer in there. Otherwise, we would have used those existing formats already. So yeah, there are things that can be used cross-discipline, and there are things that are more to kind of help operations smoother while exposing the content and making them more accessible to everyone.
Do you think there's some way though that, I mean, I don't know if you've thought about like releasing training materials or something so that people who are social scientists trying to look for archived material of some event or something can basically learn this and query archives the way that archivists do? Something that bridges it. It's not just within your own community, but something that.
That's a very interesting question, and I think you are giving Dr. Nelson ideas for next round of funding applications. Obviously, in the past, there have been effort in, I think there were IMLS funds given to folks in Canada in association with some other people. It's called Archives Unleashed project, and there were some other people involved. I think ODU was also involved in some of that work to kind of create classroom material or training material for people to learn about. The thing is, as we are moving to born digital era, everything is becoming like internet and archive, and we are leaving those paper printouts behind. It's becoming more important for the digital librarians or researchers to know how to navigate through these new systems that we have in place. And there are training materials available. IIPC, which is International Internet Preservation Consortium, is an international organization. Most of the European countries have membership in there. US, ODU is a member of that. And so sometimes they have projects for creating training material. In fact, they have a special interest group whose job is to kind of work towards creating training materials and educational materials on this thing.
Not to push it, but I think one of the things too that we struggle with, even for modeling and simulation, to make it accessible to social scientists and humanities scholars, is also the interface, right? Like there's also the reality that a lot of us don't have the time to learn yet another interface, and finding some way to make this the back end so that.
Obviously, you don't want to deal with this, right?
But thank you. Thank you.
So good folks at Lionel have something like this, which is more easier to explore and kind of it summarizes things better.
All right, Dr. Weigle?
Sure. Can you go to slide 69? This is looking at the voids profiling.
69, yes.
So I see that you've highlighted the middle row here with the 8.42% savings. So can you talk a little bit about the trade-offs that led you to highlight that one instead of the, you know, that top line there that has almost 65% savings?
Mm-hmm. I think since it was based on, so one table that we did not show, let me actually go to that. And the reason will be clear why I did it this way. So in backup slides, I have this where I have like breakdown of status codes over time. Sorry, responses that belong to one status code or the other. On the right-hand side, the table that I have, it tells fluctuations in a status code. So there is a huge number that has always been 404, right, on top. And there is a significant portion that is always been 200s. But the third row of the second table, which is 36,000 or so, which is actually about 5% or 6% of the row prior to that. In the period of about from mid of 2016 to 2019, so that's basically 17, 18, 19, 3.5 years period, there were 5% resources that were at some point 404, but they changed to 200, right? And since it is a usage-based profile, unless you allow periodic updates of your White's profiles, more aggressively looking at it, you would have missed these things because you learned initially like, yeah, those are 404s, and you did not look back at it, right? Although in that evaluation, I only reported things that have always been 404s. They have never returned anything other than 404, so that number is different. But what I'm saying is, if it is reporting 404 now, there is no guarantee that it will be 404 2 months later or 3 days later. So that's why we gone to things that were like more frequently accessed. And another aspect to that is if something is not accessed very frequently. So that was slide number 64. What was that?
69.
69.
You're in the 90s.
Yeah. 69 right here. Okay. So one thing I mentioned somewhere, I think in the slide after that, is you don't want to profile things that are not very frequent. So sure, we were going to get 64 or 65% saving, but the number of keys that you'll be storing or URIs that you'll be storing is 13.6 million or 13.6 million URIs that you'll have to keep track of. Here, we are only talking about 2.4K actually.
But I mean, wouldn't some of these roll up? You know, you wouldn't really have 13 million entries. You would have a fewer number.
Right. And so that is also something that is described here. Use specific keys with only high confidence.
Mm-hmm.
The reason is if you roll up, then you are giving chance of false negatives to leak in. You are saying they never appeared, okay? So for example, let me give you an example. You got cnn.com/foo 404, cnn.com/bar 404. You said, hey, we are getting foo and bar and bears all 404. Let's say cnn.com.star is 404, okay? So you reduce that to a smaller number, and now all those good things that were actually present, you are introducing those. So in archival voids, we really need to be very, very strict in like, we only use like longer keys and things that are more frequent. So it's again, there are costs associated with these things, like how often you are going to update these things. If you update more frequently, then doesn't matter.
Right. So, but then so if there's an archive that's doing both its holdings profile and its voids profile, or you're a third party that's essentially creating these profiles. Is there some cooperation between them? So if you do your holdings profile first, would you then create the voids profile with some knowledge of what's in the holdings profile, just to, in terms of rolling up, just for your CNN example?
Yes, that's an interesting point. The thing is, what you really need to pay attention to is whichever key you want to win, you want that to be the longest, because in the inverted index, when you are matching and trying to find something, you'll find a lot of prefixes that you'll find com comma star that matches, com comma CNN comma star that matches, com comma CNN / news / star that matches. You'll have many sorts of matching, right? What you are looking for is the longest matching patterns for each archive there, right? So if you want the 404s to win, you want that key to be longer than any positive that is reported. And if you want the holdings to win in some situations, so there is like dependency, of course, the system does not stop people to kind of come up with more clever ways to optimize that. But I think it is a lot easier to create holdings independently, because data sources for holdings are different than data sources for voids, right? And if you make too much interdependency in there, the problem is people who are kind of consuming these profiles, downloading periodically, they will have hard time keeping things in sync, actually. So our advice generally is to keep the holdings profile more aggressive, in like, more lenient, and in voids profile more aggressive, but more frequently updated, and keep them separate so that people can just periodically poll voids profile while they can rest with the holdings profile for longer. Generally, that's the advice. But yeah, what you are pointing to the right thing. It is doable, and there can be some approaches. In fact, in the resolution mechanism, I already have those techniques in place. It's just that we never talked about what kind of jugglery that can be done to synchronize these generations.
Okay, I have another question, and this is on slide 94.
Mm-hmm. Slide 94. Yes.
So you made the comment that archive.org isn't profiled and gets a default routing score. Mm-hmm. And so is this default routing score specifically configured for Wayback Machine because you know about it?
So this is only needed when you are aggregating things, right? When you are talking about scores for individual archives, you don't need this, right? I mean, you can have anything. When you are putting things in perspective and you are trying to create like a list of archives in a like ranked ordered list, basically, that's where you want to include stuff. In my thesis, I have a code example there where I have given order of preference, like, hey, if neither voids nor holdings are profiled, then pre-configure some default score and assign that, so that if you're dealing with like 15 archives and you have only profiled 3 with voids, 2 with holdings, and 2 with both holdings and voids, in what order you'll specify a default score and how you'll update it. That's actually described in a algorithmic fashion in the actual dissertation. But,
okay, so
but yes, it's something that you want to assign so that you do not want to profile things that you already know they have a lot of things. So you can already give some score to that, right? And like.
Well, right. So I mean that was my question. I mean, is the score here specific to archive.org because you know that it has lots of stuff, or if I started up a new archive and didn't have a profile about it, would I get the same score as archive.org, or would you give me some lower score because I probably have a small set of things archived?
So that will be, I think, based on the domain knowledge of the person who is configuring, and they should they should generally give like a lower score to newer archives where the confidence level is low, basically. And it can also be configured. So here is another thing. Even if you give default score to 1 for all the new ones, you can actually fine tune in weights. So let me go to there is this slide. So here what we have is when you can specify weights to each archive, right? And as I said, for the same score, one archive performs better than the other. You can, you can basically, even if you give default score to everyone the same, at the aggregation time when you are doing like weighted relative routing score, at that time you can adjust these biases, like give Internet Archive weight of 5 and others weight of 2 or whatever.
So is there if some archive doesn't have a profile at all, why would you not just broadcast? Why would you not just broadcast to them?
Yeah, just give them a score of 1 and that will be broadcasted there. Like, I mean,
well, I mean, you know, that gives them the incentive to create a profile, right? If they're, if you know, there's too much traffic coming to them, hey, there's a simple answer, right?
And that's the point here, is things that we have not profiled, that we don't know about whether they have or not. And if the point is to collect from them, then give them default score so they are in the list, and an aggregator can decide for those default entries that they can. In fact, this result can further be annotated with another attribute where we can specify like, hey, this is not profiled, or this is profiled with voids, and this is profiled with, so that basically all depends on how much information we want to expose via this interface, you know, and then you know, consumers of this API can make more informed decision choices, basically.
Okay, and so then one last, this is related. So if you're using this and you send a query, and the query only goes to a select set of archives for a particular URI, and you get 0 results back, but there's some potential false negatives. So what should happen then? I mean, are you gonna just accept that, oh, you know, the archives that I think had it don't have it, so I'm done?
So, I mean, I think in MemGator's repository, Matt Kelly had a ticket a while ago. He was thinking like, hey, can we just stop the first time you get a response from somewhere, like keep asking everyone, and then the first time you get from response from somewhere, just bail everything out and just live with that. That's another possibility, I think. So if it's the cutoff score is based on the end user of this API, right? So if they decided that I'm going to go for this cutoff, and for that they are getting more non-results and over the time. So I think somewhere in the thesis I also described that periodically you should check for things that you would otherwise not route. Your system is saying not route, but you route to that and learn from their holding, so that you can update your information over time. Otherwise, you will be in this self loop, especially if you are observing from outside, that you are a usage-based profiling, basically. In that case, it's tricky that you said, first time I checked for last 4 years and I never found anything, and now I'm set that this archive doesn't have anything about that. And if you never check that again, then you are in that loop of, hey, they don't have it. So there are numerous ways to kind of, I think, handle that. If your scores are not giving good results, then you lower your cutoff score and try again, or things that you did not. Now, the thing is, you don't want to do it incrementally in the same request. Otherwise, delay will increase. So you made request to 3 archives, okay? And you waited for their response, and everyone said, I don't have it. Then you make 2 more requests to 2 new. Then user is waiting for 5 more seconds, basically. And that's not a good experience. But again, it all depends on your application. If you're not directly giving response to a user, you are running a script to kind of download from places, then perhaps you can go for this compromise.
Okay, thanks. Yeah. That's all I had.
All right, Dr. Wu.
Yes. Okay, I have a few questions. Looks like they're simple. The first is how hard it is to make the MementoMap sustainable.
Sustainable?
sustainable? Means that like, how do you plan to keep it running for a long time?
So MementoMap is just it's not a service. MementoMap, MemGator is a service. MementoMap is kind of here are a bunch of scripts. You give me input based on your CDX files or access logs, or I can do full text searching to learn about it. And it is like one-time job, and you got a file. That file you host it somewhere, and you advertise it using the dissemination mechanisms like well-known URIs or link relations. And
so
all.
If it is not a service, it is an algorithm, or shall we classify it as an algorithm, or is
so MementoMap
MementoMap
is a framework. MementoMap is also a software named MementoMap, which generates MementoMaps. So MementoMap is a file as well. So MementoMap, the file, is more like, say, robots.txt is a file, which changes once in a while, but doesn't change very often. It's same as, you're very familiar with sitemaps.xml, right? Sitemaps.xml is not a service. It's just a file. When a web archive or a host thinks that they have enough new material, they want to update their sitemap, they can update that, right? That's the idea here as well. So here is another thing. If you make your MementoMaps shorter, like keys will be smaller, don't go for too much detail, then it won't be stale very quickly. So if you have like CNN.com and no further details on that, you just have like, I have like 10,000 mementos that fall under CNN.com category. You do not specify any paths or anything. Then in the future, as you crawl more CNN.coms, you don't have to update it very often. You already have it like, at a summary level. But if you go all the way in further detail, the size will increase, the accuracy will increase as well. So there is this inherent cost. You make the keys smaller, the update frequency will be like, it won't go stale very quickly. Freshness will last. But then it will introduce more false positives because you have like a higher level summary.
Okay, well, that's good enough. Thank you. Next question is you're calculating the routing scores. So what's the overhead to calculate the routing scores if the number of archives is bigger?
Not a lot. Let me go to that slide actually. That says right here.
And is the score query dependent or is query independent?
So there is one aspect that is query dependent, and there is other aspect that is query independent. So there is the density score is pre-computed. Density score is basically when you generated MementoMaps. That is so here in MementoMap files, we have number of URIs and number of URIMs under each URI key, okay? And this is kind of one-time pass. So from here, when you generate, what we call it, the when you generate from MementoMap, so here is MementoMaps. And in this case, we have something called, if you see the fields attribute here, there is keys are certs, values are frequency. So frequency is something that defines how many mementos and how many URIs are there. So this is kind of one-time processing. You got those numbers in, unless you want to add some more stuff or compress it further. You don't have to update those scores. With these numbers, knowing URIs or URIMs, the formula that we described above for density, you calculate density and you create these inverted index. This is again one-time job. You only have to update it when you have more MementoMaps to ingest. Once you do this, these numbers like 0 or 0.2, 0.08, all these things, these are the density scores. So this is pre-computed. This one is pre-computed in this case when you are creating inverted index.
So mu is pre-computed, right?
Yes. Chi is dynamic. It depends on when someone performs a query, you need to check that, and you perform a lookup in your inverted index and find what is the longest.
And L is the length. So L is the length, right?
Say it again.
L is the length.
Yes, L is the length.
or-
LK is length
okay,
of
so
the
it is
key.
query dependent.
Yes,
Okay,
this one is
so
query
it is query
dependent.
dependent.
Yes.
Okay, okay, I got it. So
Yeah,
that's
but
it.
the
So-
calculation is very simple. You see there, you just have to have like,
yeah.
count their lengths basically. That's all.
So given the randomness of this, the query and also the archival collection, have you considered a Bayesian method on this,
Say it
which
again?
you can calculate considered a Bayesian method? You
For
can
doing what?
have so you can calculate a prior probability, and then based on what you have, you can have a posterior probability that's correct your prior probability.
Yeah, but then we don't know which query URIs will be hitting, right? Unless we know that. That's why it is calculated at then and there. The routing score is calculated at that time. In fact, in the Bayesian classifier method, here when we reported data, we did not provide,
but this is classification, right?
Yes.
This is classification.
Yeah, but
and
yeah, but
you're on naive Bayes.
Yeah, this is naive Bayes.
What's
yes.
the method for this? Okay.
Yeah, naive Bayes.
The naive Bayes is different from the Bayesian method I was mentioning. The first one is a probability method, but this one is machine. It's a classification method, assuming that so the features are independent. Okay, so I think I'm okay with the last question. So about the machine learning one, so what are the features you are using for the classification tasks?
Yes.
And how are the ground truths compiled?
Yes. So let me tell you the features that we were using. So so the stuff that we used was all the parameters that we are supplying here. In fact, if you go to here, in the result, we are using the length of the URI key. We actually reported this. So in this thing on top, we have lookup URI, lookup key is basically from lookup URI, what is the minified version, the query parameters is stripped off and all, that becomes URI key. And then lookup key length, this number is something that we feed as an attribute. Other thing we feed is when there is a match, the length of the URI key that was matched in the archive, that we feed. We also feed the density score. We do not provide the difference in the keys, because that's something that it already has that information. It can figure those things out. So all the derived attributes that we have, we don't supply that. We provide the basic raw thing. We also supply the number of URIs in the archive. So basically the same information we use to come up with our heuristic routing score, we are providing the same information to machine learning system and see how it performs there basically.
Okay, and how big is the training set?
I think it was 1 million URIs.
Okay,
yeah.
You don't need that much, but for a Bayesian method, you don't need that many. Okay, but that's good.
Yeah, because
so
the thing is,
question...
that's the data set that we use for our other evaluations. So in fact, in the past also, we used like 1 million URI samples from 4 sources. This was the 5th source that we used. And we thought like, hey, why not just use that?
Okay.
So we did like, 10-fold cross-validation on that.
Okay. So the last question is about the coverage of study in terms of language. It looks like that you, so this is open language, right? But for the random key phrase queries, I guess you are limiting the language to English, or no?
Oh, you are talking about random searcher model. Okay, got it. Let
yes.
me go there. Right here, yes.
Is this limiting to English website? Or?
No, that's the point. Our system is language independent actually. So if you provide static files, a static list of queries, in fact, this is what we are evaluating here. So static mode, in that case, you supply a list of keywords, okay? In the other 3 approaches, popularity biased, equal opportunity, and conservative, these approaches are demonstrated here in random searcher model. In fact, the tool works in either way. You configure it how you want it to behave. So in this case, you just need one starting keyword, and from there it will just run on its own. So you supply just one keyword to.
Okay, but what if the page you get is not in English? Then you still randomly pick a word from that page?
Absolutely, that's the point. Without knowing the type or nature of the collection, this random searcher model will discover whatever is in there. If the word belongs to that collection, the point here is searching for a keyword. It's like you are creating a network of web pages that are not connected with links, but they are connected with co-occurring keywords. So if I search for car and I found 5 pages, and then in one of those pages, there is a term called motor. And if I search for that, I will get 20 pages. And some of those will be from the previous results, some will be other. So you navigate through the dense network that are connected with co-occurring keywords. And that's how it sails through the collection.
Okay, but you need a tool to parse the web page, right? If it's not English, let's say if it's Chinese, how do you parse the page and get the next word?
That's an implementation detail, obviously, yes. And I think at that time, you can leverage whatever is the tokenization method available in specific language. I know in some language it's more difficult than just splitting on spaces, but that's not something that I think I would worry about. That's an implementation detail, obviously, and it's just a matter of what we evaluated on was Archive It search engine, and they were like English and some mix of some other languages. That's all we had.
And some of those collections are mixed languages too.
Right.
Okay. Thank you. I'm done with my questions.
All right. At this point, we'd ask everyone not on the committee and not sued to leave at this point.
So thank you everyone for attending.
We'll give you a second to log off, and then we'll start kicking people off.
See you later, Sawood.
We'll wait just a few more seconds for everyone to log off here. We can figure out who logged in and then just went back to sleep or something.
Let me see. Okay.
Do you want to stop recording at this point, or?